Hello! In this video, we are going to prove the following theorem. Suppose f is a function from the closed interval a comma b to r, and f is continuous on a comma b. Then, f is uniformly continuous on a comma b. Now, let's first remind ourselves the definition of what it means for f to be uniformly continuous on a comma b. It means the following. It means for every epsilon greater than 0, there exists a delta greater than 0, such that for all x and y in the closed interval a comma b, if absolute value of x minus y is less than delta, then absolute value of f of x minus f of y is less than epsilon. Now, in proving this theorem, we are going to be using the sequential criterion for continuity, which tells us the following in regards to our function f. Given c is any element of a comma b, then f is continuous at c, if and only if, for every sequence x1, x2, x3, and so on, in the closed interval a comma b that converges to c, we have that the sequence f of x1, f of x2, f of x3, and so on, converges to f of c. We're also going to be using some properties of convergent sequences. For example, if we have a convergent sequence such that all terms of the sequence are between a and b, then the limit of the sequence is also between a and b. Another property we're going to be using is the squeeze theorem. Given three sequences of real numbers, xn, yn, and zn, such that xn and zn are convergent and converge to the same value, and we have xn is less than or equal to yn, less than or equal to zn for all positive integers n. Well, then it follows that the sequence yn is convergent, and all three sequences converge to the same value. We're also going to be using the notion of subsequences in proving this theorem. And the idea of a subsequence is as follows. If we have a sequence of real numbers, x1, x2, x3, and so on, and we have a strictly increasing sequence of positive integers, n1, n2, n3, and so on, well then the sequence xn1, xn2, xn3, and so on is a subsequence of this sequence. Now, a property of subsequences is that if we have a sequence x1, x2, x3, and so on that converges to a real number x, well then all of its subsequences converge to x. Another property is that every bounded sequence has a convergent subsequence. This result is often called the Bolzano-Weierstrass theorem. Okay, so now let's get into proving this theorem. Now we're trying to prove that f is uniformly continuous on a comma b. And to prove that, we'll assume for a contradiction that f is not uniformly continuous on a comma b. Well then, in other words, we're saying that the negation of this statement is true. And the negation of this statement is to say there exists an epsilon naught greater than 0, such that for all delta greater than 0, there exists elements x and y in a comma b, such that absolute value of x minus y is less than delta, but the absolute value of f of x minus f of y is greater than or equal to epsilon naught. So then this statement is true, and it works for every positive real number. So what we're going to do is we're going to consider the positive integers, and we are going to apply the reciprocal of each positive integer to this statement. For example, if we consider the positive integer 1, we're going to apply the reciprocal of 1, to this statement. Well, in that case, there exist elements, I'll call x1 and y1, in a comma b, such that the absolute value of x1 minus y1 is less than 1, but the absolute value of f of x1 minus f of y1 is greater than or equal to epsilon naught. Similarly, if we consider the positive integer 2, we're going to apply 1/2 to this statement. Well, in that case, there exist elements I'll call x2 and y2 in a comma b, with a property that absolute value of x2 minus y2 is less than 1/2, but absolute value of f of x2 minus f of y2 is greater than or equal to epsilon naught. So in general, if we consider an arbitrary positive integer n, we are going to apply this statement to its reciprocal 1 over n. Well, in that case, there exist elements I'll call xn and yn in a comma b, such that absolute value of xn minus yn is less than 1 over n, but absolute value of f of xn minus f of yn is greater than or equal to epsilon naught. So this gives us two sequences of real numbers, x1, x2, x3, and so on, y1, y2, y3, and so on. Both sequences which are contained in the closed interval a comma b and satisfy these two inequalities. Now, since the sequence x1, x2, x3, and so on is contained in the closed interval a comma b, well, certainly that sequence is bounded. And since it's bounded, well, by the Bolzano-Weierstrass theorem, we should be able to find a convergent subsequence, xn1, xn2, xn3, and so on. And since this subsequence is convergent, it must have a limit, and let's call that limit c. So what's going on here is we have a subsequence, xn1, xn2, xn3, and so on. And by definition of a subsequence, we are inherently given a strictly increasing sequence of positive integers, n1, n2, n3, and so on. So then if we consider these positive integers and send each of them into the sequence of yns, well, then that will give us a subsequence yn1, yn2, yn3, and so on and so forth. Now we know that this sequence converges to C, but the claim is that this sequence will also converge to C. And we should be able to show that using the fact that this inequality is satisfied for all positive integers. Since this inequality works for all positive integers, then in particular, if we consider an arbitrary positive integer k, well then nk is a positive integer. So replacing n with nk, we have absolute value of xnk minus ynk is less than 1 over nk. So given any positive integer k, this inequality is true. And we know that absolute value is greater than or equal to 0. So then, this tells us we're in a position to apply the squeeze theorem. To do so, we know that a constant sequence of zeros converges to 0. But does the sequence 1 over nk converge to 0? Well, we know that the sequence 1 over n converges to 0, and therefore, its subsequence 1 over nk must converge to 0. So since both of these sequences converge to 0, it follows that the sequence in the middle must converge to 0 as well, by the squeeze theorem. But when a sequence of absolute values converges to 0, that implies the sequence itself converges to 0. So this implies that the sequence xnk minus ynk must converge to 0. But when the difference of two sequences converges to 0, and we know at least one of the sequences converges to some value, it follows that both sequences must converge to the same value. So since we know xnk converges to C, it follows that the sequence xnk and ynk must converge to the same value. And so this shows that both subsequences converge to the same value. But then let's note, since all terms of the sequence of xn's and the sequence of yn's are between a and b, it follows that all terms of the subsequences are between a and b as well. So it follows the value they converge to must also be between a and b. So c is between a and b. And now, since f is continuous at every point in a comma b, then in particular, f is continuous at c. So we're in a position to apply the sequential criterion. By the sequential criterion, since the sequence xn1, xn2, xn3, and so on is contained in a comma b and converges to c, it follows that the sequence f of xn1, f of xn2, f of xn3, and so on will converge to f of c. Similarly, since the sequence yn1, yn2, yn3, and so on is contained in a comma b and converges to c, it follows that the sequence f of yn1, f of yn2, f of yn3 will converge to f of c as well. So since these two sequences converge to the same value, their difference must converge to 0. Now remember, the whole goal has been to reach a contradiction. Now, with this sequence converging to 0, and this inequality being true for all positive integers, we should be able to reach a contradiction. Since this inequality is true for every positive integer, well then in particular, if we consider an arbitrary positive integer k, well then we know that nk is a positive integer. So, since this statement works for every positive integer, it must work for the positive integer nk. So replacing n with nk, we have that absolute value of f of xnk minus f of ynk is greater than or equal to epsilon naught. And we should be able to use this to show that this sequence does not converge to 0. Because, by definition of limit of a sequence, to say that this sequence does not converge to 0 means the following. It means there exists an epsilon naught greater than 0, such that for all positive integers h, there exists an integer k greater than or equal to h, such that the absolute value of f of xnk minus f of ynk is greater than or equal to epsilon naught. So all we've done here was we negated the definition of the limit of a sequence. And we can see that this statement is true, because all we do is we take epsilon naught to be the epsilon naught that we have in our proof, and then we would give ourselves an arbitrary positive integer h, and then we would take k to be h, and with h, we want to show absolute value of f of xnh minus f of ynh is greater than or equal to epsilon naught. But remember, this statement works for every positive integer k. So in particular, it must work for the positive integer h. So this inequality is true for h. And therefore, this statement is true, which means this sequence does not converge to 0. So the sequence converges to 0, and it doesn't converge to 0. So this gives us a contradiction. Our assumption that f is not uniformly continuous on a comma b led us to a contradiction, so we must instead have that f is uniformly continuous on a comma b. And so this completes the proof. And so yeah, that's pretty much it for this video.